Good afternoon and welcome to the webinar, everyone. I'm Josh. I'm going to be your host doing some of the logistical things while our presenters can focus on delivering you the message. The presenters here today are Jeff Baxter, who's here with me in the Exton office for AGI. Jeff heads up our engineering department, and he's going to be doing the first half of the presentation. And then with us on the line is Joshua Edwards, Senior Application Engineer from Phoenix Integration, and he's going to be taking over the second half of it. So with that, Jeff, hand it over to you, and you guys do your thing.
All right. Thank you, Josh. And thanks to Joshua for joining us from Phoenix Integration. Today's topic is going to be connecting engineering and mission analysis to systems models across the lifecycle. I definitely want to encourage any questions throughout today's presentation at any time. Please enter those in the chat. Joshua and I will be ready to answer them at the end of the webinar. So today's webinar is part 2 of a 4-part series focused on digital mission engineering. And in part 1, we introduced what digital mission engineering is and why it's important. So this webinar will then begin to answer the question on how to apply digital mission engineering. So for those of you that didn't see the first webinar, or even for those that saw it, we're going to do a quick recap on the what and the why, and then quickly move over into the how. So we'll first discuss, after the recap, we'll discuss STK Systems Toolkit and how you can build mission models very quickly using STK and how that fits into the overall digital mission engineering ecosystem. And we'll introduce a quick demonstration that we'll be building on throughout the course of the webinar series and focusing it on constellation design in this first webinar. I'll then pass things over to Joshua at Phoenix Integration to give an overview and demo of integrating the STK mission model with an Excel cost model and running architecture trade studies using ModelCenter. And from there, we'll share some industry examples of folks already using these tools to get today. Then we'll do a quick wrap-up and a summary and move into Q&A and talk about the rest of this sessions where we're going to be focusing heavily on SysML model integration as well as engineering simulation with Ansys. So let me start today's webinar by defining what digital mission engineering is. So really what the definition is the use of computer-based modeling, simulation, and analysis tools to design, build, and operate systems to achieve mission objectives. And it's bolded there at mission objectives. It really is all about the mission. These programs, these systems are created in response to a need or a requirement or a gap that is needed to achieve some desired mission objective. So we really want to put the focus here on the mission. And the reason digital mission engineering is so important right now, and really all the digital transformation initiatives going on in the industry, is that our competitors and adversaries are rapidly advancing their capabilities and becoming much more sophisticated. And as a result, the missions are becoming more complex, the systems are becoming more complex, and the engineering processes are more demanding to deliver those systems. And at the same time, you also have customers that are demanding more advanced missions and requiring delivery at a much tighter timeline. And so the graphic here kind of illustrates that with complexity on the y-axis you see is increasing, while delivery time on the x-axis is decreasing. So that's really what's causing the need for this digital transformation, is to deliver the most more complex capabilities and systems more rapidly. And so one of the biggest challenges in doing that is the ability to influence outcomes. It significantly decreases over time. And so if you identify critical issues later in the program lifecycle, your ability to change them actually decreases significantly. So this really applies to any phase of lifecycle, whether you're designing a new system or planning an operational mission. You need to identify those critical issues as soon as possible so that you're able to still deliver an effective solution after identifying those critical issues. So let's start by looking at an example program lifecycle. And here it all begins with, again, the mission, the customer identifying a capability gap or a mission need, at which point the next step is to come up with a conceptual idea to then meet that mission need. And that should then flow throughout the entire rest of the program, from system requirements and early design to detailed engineering design, implementation, all the way through testing and operations and sustainment. And what we see today across the industry is a lot of isolated models, a lot of reinvention and stovepipe tools, and not really a common thread across the entire program lifecycle. So starting at the concept development phase, there are typically some basic mission models that may depend loosely on physics to help understand the overall concept of the system. And as the program matures, a new mission model is created to handle more of the detailed physics models. You see there's broken lines there indicating there's typically multiple tools that are used to perform specific functionality for their areas of expertise. And then these models are then ultimately used to define the requirements thread, which is then used throughout the rest of the design, implementation, manufacturing, and testing. And this is the part of the program that is typically furthest separated from the mission model and the mission need. And so once the system is finished, the new mission models will then be created to then test and see how well that built and delivered system accomplishes that mission. And there's typically a new mission model for this, and the same thing happens in the training, operations, and sustainment areas. And so as you can see, this leads to typically a lot of isolated tools, reinvention of the wheel, and it makes it very hard to tie everything together. And the thing that compounds this problem is this is just talking about a single program or a single project. And when you get additional projects or programs, even if they're very similar, you kind of go through this same process from beginning to end as well. So the vision of digital engineering is to have combined, integrated, and persistent models throughout the program lifecycle. And in order to do that, you need to have a good mission model that defines how effective your system is at meeting the initial mission needs at the beginning. So from there, you can define your system model, your subsystem model, platform model, component model, all the way down to the component model, and as you work through the rest of the program lifecycle. And in order to have an enduring, authoritative source of truth, you need to tie all those models into a multi-domain physics environment. And another aspect is that it's important to, as we discussed earlier, to identify those critical issues as early as possible. And so bringing as much of that fidelity as early as possible into the life cycle, ideally during that concept development phase. So that can be done by either using the higher fidelity tools earlier in the process or by using previous models for existing systems. And finally, another important aspect of the digital engineering is the concept of a digital thread. So you can think of each of these models as individual strands, and for all this to work together, they need to be integrated like a thread. So that way, when you change individual parts of one model, it pulls through the rest of the models as well at any point in the life cycle. And in the previous webinar, we discussed and we quantified some of the impacts of not applying digital mission engineering, which mostly fell into three high-level categories of tool reinvention, model recreation between those different phases, and lack of tool integration. And in the webinar, we discussed how addressing these issues can accelerate the timeline by a factor of 2.5 to up to 6 times. So that's, again, kind of the what and the why of digital mission engineering. So now what I really like to focus on is the how. So how do we go about doing this? And although the digital engineering initiative is still fairly new, AGI has spent the last 30 years developing a digital mission engineering framework, what we call STK, Systems Toolkit. And STK allows you to quickly build computer-based models of platforms and their performance, sensor models, communication models, threat models, and the environment model, and bring those and combine them into a physics-based multi-domain system of systems, simulation, and analysis environment. And underlying this framework is a time-based geometry engine that provides a common reference frame for time and coordinate systems that allows us to analyze all of these different systems in the same environment. And also, STK has a modern search, version control, security, and scalability environment that helps you manage your modeling and simulations. And most importantly, STK allows you to calculate over 40,000 metrics out of the box that quantify that mission effectiveness. And you can then output those parameters as text reports, as graphs, as surface plots, as you see here, or communicating the mission effect in terms of images and videos showing the systems performing in a mission environment is very, very powerful and compelling. And so while that is a lot and it covers a lot, it is still, there's always going to be a need for additional customization on top of what's commercially available through SDK. So that's where SDK has an open API and where it becomes easy to extend, customize, and integrate with other industry standard tools, programming environments, and other data formats as well. So to help illustrate how SDK can be applied to digital mission engineering, we've come up with a notional demonstration that we'll be building throughout this webinar series. And the objective of this demo is to design a cost-effective constellation of satellites that provides communications, missile defense, and Earth imaging. And the requirements here that we're going to look at in this webinar are the communications, and specifically, we want to provide 24-hour continuous communication over a selected group of ground locations. And we're going to design this with a series of constraints listed here, which are 1 to 5 orbit planes, 1 to 5 satellites per orbit plane, and vary the altitude between 500 and 1,000 kilometers with a payload field of view of 110 degrees. So let's go ahead and start building out this scenario. And to help illustrate the time savings and how quickly you can build up these mission models, we're actually going to be building this from scratch. So if you're new to SDK, it has an integrated 3D graphics and 2D graphics environment and allows you to bring in a wide variety of systems. So aircraft, satellites, missiles, ground vehicles, ships, as well as ground targets, and then attach all of the payloads to those, sensors, communications equipment, radars, and there's a variety of methods for doing that. So for a satellite, in this example, we're going to use the Orbit Wizard, which allows us to select from a list of common satellite orbit types. In this case, we'll just do a 1,000 kilometer circular low Earth orbiting satellite as our initial satellite for consideration. And here we can see the satellite in the 3D graphics window, the ground track in the 2D graphics window. And now we can insert our payload. And in this case, we're going to do a pretty simple geometric field of view, and we're going to give it that 55-degree cone half angle based on our mission requirements. And from here, you can see the sensor field of view. You can see the footprint on the ground, which is the areas on the ground that we can communicate with. And you can then begin to play through the simulation, and you can see as that satellite orbits, as the footprint changes over time. So we're going to go ahead and bring in a target deck, and in this case, we just have a group of the top 15 most populated cities in the world, and we want to look at how well we can communicate from our satellite to those ground locations. How often can we see those points? We can visually inspect the scenario and see we've got a certain amount of coverage, but what we want to do is really calculate and quantify that mission effectiveness. So how long can we see those ground targets? And the way that we're going to do that is by grouping all of the targets together in a collection, which we use a constellation object, and a grouping of all of our sensors. Now, right now, we just have a single sensor, but we're going to quickly look at other satellites with additional sensors soon for later. And then what we can use is a chain object, which is a very powerful object in SDK that allows you to perform this group analysis from one grouping of objects to another grouping of objects. You can have multiple hops, you can have different constraints. In this case, when does my sensor see any of my targets? And then I have a variety of data providers I can choose from, such as when can I see any of these targets? But more importantly, what we're interested in looking at is when can I see any of the targets throughout my entire 24-hour time interval from any of my sensors? So this graph is now showing you all of the communication times and all of the gaps. So the gaps are just the empty spaces, and the communication times are the green bars. And so what we want to do is design a system that has continuous 24-hour communication over the entire scenario. So to do that, we're going to do a quick design orbit trade study where we're going to vary some of the orbit parameters of our satellite that we built from pretty much default settings. So here we can use Analyzer to select any of the inputs from SDK and any of the outputs from SDK, and then run a wide variety of trade studies on those inputs and outputs. So the input that we'll look at here is our satellite's inclination, and the output we're going to look at is the total duration of the contact times from our sensors to our ground targets. And then we can define starting and stopping values for that inclination. So in this case, we'll look from 0 degrees to 90 degrees of inclination, and we'll do a step size of 5 degrees and see how that impacts our overall communication times. And so we can see here as the trade study begins, you can see the plots returning results, and you can also in the 2D window see the orbit ground track changing as the trade study is executing SDK in the background. And here you can see the data again populating the scatter plot, which is showing me my best communication time at a given inclination. So that's a very quick trade study inside of SDK, and what we want to look at is the extending that to multiple satellites. So rather than just a single satellite, which can't provide complete 24 coverage, let's create a constellation of 25 satellites. Let's look at the max conditions, and let's create a Walker constellation, and let's see how well that performs against it. So here we just created the Walker constellation. It inherited the same sensor from my original satellite, and I can then animate my scenario to see what that looks like and what that coverage looks like. So the thing we need to do now is update our grouping of sensors to include all of those satellites, all 25 of them, and now we can simply refresh our report and see if we got that continuous communication, which it looks like we did in this case, that we have a solid line, meaning we have communications at any particular time. And then furthermore, we can visualize that with the yellow lines from the ground targets to our satellite constellation. We can begin animating and getting a visual understanding of the design that we came up with that meets our communications requirements. So this was a very quick example of using STK to provide that mission model to design your satellite orbits, your payloads, and quantify that mission effectiveness of how well can I cover all of those ground targets. And while this was a good, quick notional example, it didn't really get into that trade study to answer how many satellites did it actually take. And we looked at 1 satellite and 25, but we now want to explore that trade space a little bit more completely. And we want to look at other factors such as integrating maybe a cost model. Just because all of these satellites can provide it, that doesn't mean that this is the best design. So at this point, what I'm going to do is I'm going to go ahead and turn things over to Joshua at Phoenix Integration.
Thank you, Jeff. My name is Joshua Edwards. I'm a senior application engineer from Phoenix Integration. I just want to thank AGI for having Phoenix and myself on this webinar. All right, so let's hop into it and continue on the great demo that that Jeff just gave for SDK. So first off, I just want to level set the audience. So if you've ever attended a Phoenix Integration webinar before in the past, you may be very familiar with this image. This is something we use to give everyone an understanding of what ModelCenter does. And so this is an image of a symphony orchestra. It's comprised of expert musicians who are very talented in their craft, but it's also made up of a conductor. And so the conductor themselves don't play an instrument, but they are very vital to the orchestra in that they conduct and keep the rest of the orchestra in sync and produce a harmonious result. So what if you had a conductor for your engineering tools and analyses? You'd be able to keep them in sync and keep them working together so that they could produce a very valuable result across multiple disciplines. So our answer for that is ModelCenter. Specifically, we have 3 capabilities of ModelCenter: ModelCenter Integrate, ModelCenter Explore, and ModelCenter MBSE. And so what I'm going to do is I'm going to dive a little bit into each one of these just to give everyone an understanding of what each capability does, so that there's understanding and then we'll move into the demo and you'll be able to understand where and which pieces are working together. So to start out with ModelCenter Integrate, ModelCenter is a vendor neutral tool, so we're able to run anything with a API, badge command, scripting, up to allowing users to develop their own plugins. So you can see here in this little diagram, we have just a very small subset of tools our customers have automated, but that's not an exhaustive list. So we allow the users, or ModelCenter allows users to automate any engineering analysis tool, whether it's a COTS or in-house tool, 20-year-old Fortran code, using black box execution. So for ModelCenter Integrate to run any execution, it just needs to know how to execute that engineering analysis and which input and output variables to expose. So treating it, like I said, as a traditional black box methodology. Once we have automated a tool in this fashion, we can then integrate them together into a workflow. This is still with ModelCenter Integrate. So you see here in this example workflow, we have a bunch of blocks tied together. So each block here, as we call a component, represents a black box analysis. And then by bringing them and integrating them to the workflow, we're allowing each one of these components to pass data from each other, from one to the other. So in this case, we can see in the top left corner, the data from that top component will pass its data down to the subsequent components in the workflow. This allows for the automated execution and transfer of data for multiple engineering tools. Once we have a integrated workflow of all these components and analyses, we can then run a trade study. So this is an example of a DOE tool that we have as one of our many trade study tools. So our trade studies will drive the workflow once it's been integrated. So as you can see here, we allow the specification of your design variables and your responses. You can then set the bounds for your design variables from lows to highs. You can give them discrete options to choose from, and you can select different designs that you'd like to run. So when you do finally configure your trade study and you execute, we'll hit the run button, it will produce a table of data. So we see here in this little snippet of a table, we have 2,197 runs. Each column here, each run represents the execution of the workflow. So we executed the previous workflow that you saw 2,197 times automatically just by setting up a couple bounds, specifying design variables and the responses and hitting the run button. Moving on to the second capability, which is ModelCenter Explore. This allows you to take that data, all this large amount of data that that is produced in this table, and allows you to visualize it. So I'm going to show just a couple quick visualizations here to give a taste. One right here being a parallel coordinates plot of the data. We can do things like variable importance or sensitivity summaries of the data to show which variables are most important to which responses. And then we can see here we have a tool or a visualization called our prediction profile contour plot, where we can apply constraints and look at our design space in an interactive way, and we can move around the little black dot you see to show what that design represents and where it is in the design space. Explore also has capabilities such as response surface models, probabilistics, and optimization, but I won't touch on that at the moment. So moving into the third capability, ModelCenter MBSE. This allows the integrations of systems models, such as the one shown here. This is a parametric diagram. And so the way we do that is we connect the system model value properties to variables in a ModelCenter workflow. So one that we saw previously that we've automated and integrated, we can tie those two together and essentially tie the systems engineering world to the domain engineering world. The way we're actually able to execute this is with the tool MBSE Analyzer. And what this does is it gives a representation of our value properties here in this dashboard, allows us to modify these and give different values to our value properties. Once we've done that, we can hit the run button, and we see here that it actually, with these little arrows, will actually go and execute and build the workflow that's associated with that, with the diagram or the elements in the SysML model, Magic Draw model. Go and build the workflow using the value properties that we've specified, execute, return updated results for the responses, and then lastly, we can check to see if requirements were met. If we had satisfied relationships implemented in our Magic Draw model, the MBSE tool, MBSE Analyzer, will go and verify if those requirements were met. So we can see here represented with the green check marks and the red X's whether or not a requirement was met or failed. Other capabilities for ModelCenter MBSE include the execution of behavior diagrams, and I'll touch a little bit on that later in the presentation. So as Jeff alluded to, he integrated he developed a STK scenario. So what we're going to get into with our ModelCenter demo is actually going to take that STK scenario, integrate that in with ModelCenter, and also add in an Excel cost spreadsheet so that we can get a visualization or plot or a trade study for cost versus that access duration or that coverage of communication in STK. So if you haven't seen ModelCenter before, this is the GUI, and I'm just going to highlight a couple of the three sections here. So we see the blue section in the middle. This is what we call the analysis view. This is where we will build the workflows. Down in the bottom is what we call our server browser. You can think of this as our toolbox. So we can bring in plugins that come out of the box with ModelCenter that users have developed, or engineering analyses that have been made reusable, and they can just be dragged and dropped right into the workflow. The third section here is the component tree over to the left, and that's just going to give us a tree view or a tree structure view of the workflow. So it's going to show all the components in the workflow along with the inputs and output variables for each component. We'll be able to modify the inputs here, and then we'll be able to view the outputs after running the workflow here as well. So without further ado, I will go ahead and start the demo. So the first thing we're going to do is go down in that server browser and grab our STK plugin and specify the scenario, the constellation design scenario that Jeff had already constructed. We see STK actually launches in the background. So this will actually be performing the analyses. We can go ahead and minimize that. And just like what we saw in the STK analyzer, we're going to go ahead and select a few inputs and outputs that we'd like to vary. So in this case, we're going to bring in the inclination, but we're also going to bring in those Walker variables that define the constellation. Next, we'll look at the output. In this case, we're going to do that duration of complete access. We're going to do the total sum for that. And once we hit the OK button, we see we can rename our STK component, and we're going to call this constellation design. Over in the component tree, we can expand it to see all the variables that we've exposed to ModelCenter, the inclination, the Walker component variables, and then the sum of the complete access duration. Doing a quick run to make sure things work as expected, and we do get an output here. But next, to take it to a next level test, we're going to run that same parametric study that we saw before in STK, bringing in the inclination and bringing in the sum of the complete access duration. We're going to do a little shorter bounds on our sweep here. Just do 10 samples just to make sure we get some of the same behavior or the same behavior that we saw in SDK. So running produces the same plot just with fewer data points. So that looks like a good integration here. We're getting as expected results. And here, of course, is the table of data that the scatter plot was used to populate. So we're going to close all this. This was just to test to make sure that the integration of SDK was successful. And then next, we're going to go ahead and bring in the Excel plugin to bring in our cost spreadsheet. So we'll drag and drop that into the workflow as well, specify the spreadsheet that performs our cost calculations. And this spreadsheet has named ranges specified for cells. The plugin will go and identify those named ranges and bring those in as optional variables. We can see things here like cost per launch, cost per satellite, and ultimately we're looking at the total cost of a constellation that we like. We're going to go ahead and give some metadata to that, specifically units of millions of dollars. Apply our changes. Go ahead and rename the Excel component as well to cost. And then just for some organizational benefit, we're going to go ahead and rename or reorganize the variables so they're a little bit more intuitive with the inputs at the top and the outputs at the bottom. Next, we'll want to link these two models together. So we'll want to link SDK to cost or to the Excel. So we drag a link from one to the other. ModelCenter recognizes that we have two variables that have the same names in both components. We say we want to create those links, and we can verify that with our visual link editor that shows those links in a visual format. So we can see here in the SDK component, we have number of planes is linking to number of planes in the cost, and same thing with number of sats per plane. So now we have an integrated workflow. We can go ahead and run this as well. We see that the data from the number of planes and number of sats per plane from SDK is passed down to cost. And then now we will set a couple of initial values for our inputs just before we run a DOE of our constellation design. So we're going to bring in number of planes and number of sats per plane. We're going to bring in that sum complete access duration. And then we're also going to bring in some variables from the cost as well. So we're going to do total sats in our constellation and the total cost. We'll specify the ranges that we'd like to run for each of our design variables. So we're going to do 1 to 3 of number of planes incremented by 1. And then number of sats per plane is 1 to 5 incremented by 1 as well. So this gives us a total of 15 runs. So we hit the run button, we will execute the workflow 15 times with those different design variable values, and fast forward to the 15th run, we can go ahead and do some visualization. So we're just going to bring in a basic scatter plot and start setting up the scatter plot to do cost versus that sum of duration for complete access. So we'll switch to our total cost as the x-axis and the sum for our y-axis. And just for visual sake, we're going to give the color as total sats. We can also apply constraints to the plot. So in this case, we're going to take out some of the more expensive satellite constellation designs and also some of the lower performance constellation designs as well. And we can see here that shaded those infeasible, those are the gray points, and we're left with a subset. So we have a nice knee in the curve here. We're going to select 1 point. Number of planes is 1 and number of sats per plane is 5. Notice that this doesn't have the highest coverage here, but looking at the trend, it's looking like the best bang for the buck. And so therefore, if we wanted to increase coverage, we'd have to increase cost as well. All right, so moving forward here, that was the demonstration, but I did want to allude to a couple of use cases in industry where the DME methodology has been implemented. So this is the first webinar, I believe, that was presented in the or was discussed in the previous AGI webinar series part. So this is the Lockheed Martin OSIRIS-REx webinar. This integrates systems models with domain models, specifically SDK, using ModelCenter to determine if we violated satellite keep-out zones and if those requirements were met or not. So I'm not going to talk too much more on that since it was already presented, but these are webinars that are hosted on the Phoenix Integration Webinars page, and you can see the link down in the bottom right-hand corner if you'd like to check that in fuller detail. So I did want to talk about one more industry use case that's also a webinar that we host. So this is one that was done by Parsons. This was their Distributed Model-Based Systems Engineering webinar presented by Stephen Thomas, Albert Hemphill, and Tim Gatos. Link for that is down at the bottom as well. And so getting into the details of this webinar, I'm not going to spoil it and go into great detail, but I do want to give a little taste about what it encompasses so that you can have some interest in it and go and view it yourself. So first off, one main goal or objective for this webinar was to do distributed engineering. In this case, they had engineering sites across the United States, so not all Parsons, some supplier and technology companies as well. So we can see we're distributed between California, Colorado, Virginia, and Maryland. And so the integration of models from all sites was done into one workflow using ModelCenter's remote execution capabilities. And so they integrated systems models with domain models, including SDK as well, using ModelCenter in this fashion. So what they were trying to achieve here, or the use case that they were trying to accomplish, had to do with a satellite orbiting as well. Based off of their technical requirements document, they had 88 requirements that they had to meet. This orbital trade study here focused on 5 key ones, and those included the sun synchronous orbit, or the orbit of the satellite, the orbital life of the satellite, the requirement that we had to have 100% coverage every 12 hours, and then the type of sensor that we're using. And specifically with the type of sensor, there was a requirement that we needed to have a resolution of less than 2 kilometers. These two were the driving requirements, the 100% coverage and the resolution of 2 kilometers. The main design variable that would drive that was the orbital altitude, which they could vary from 480 to 535 kilometers. And then they were also able to look at a reaction wheel, which the logistics and the engineering for that was done by a supplier that was based in Colorado Springs, which they integrated that into their workflow as well. So the reaction wheel itself had requirements that it needed to meet given the pointing and the saturation. So just a little highlight of what they had to do, or one of the diagrams that they used. This is their parametric diagram that they used to connect the SysML model in MatterDraw to the ModelCenter workflow to calculate coverage. So we can see here on the left the value properties from their structure diagrams, or their block definition diagrams are exposed, and we've linked that over into a constraint block that has an external analysis stereotype that is pointing to a ModelCenter workflow. So we're going to feed in a couple variables from the value properties, the vertical half angle, the circular altitude, and that's going to calculate a range of responses. Most importantly is the coverage here. So in summary, after building the workflows, building the SysML diagrams, connecting the two, they were able to determine that to maintain sensor resolution and 100% coverage, which were the two main requirements, 500 kilometer orbit satisfied that, and the orbital life was 6.3 years, which was satisfactory as well. And that is it for my portion of the presentation. I'm going to pass that back to Jeff.
So I just quickly wanted to summarize today's presentation. So thank you, Joshua, for the demonstration. That was great, and good industry examples of industry already doing this today and previously, especially hooking into the MBSE part, which we are going to cover more in the next webinar. So as we discussed earlier, just bringing us back to what we talked about at the beginning, the whole vision of digital mission engineering is really to connect all of the engineering and systems models to the mission model that is rooted in a multi-domain physics environment. Furthermore, these models need to be pulled in as early as possible in the process and persist throughout the life cycle so that you can identify those critical design changes as early as possible and still be able to influence the outcomes. So we discussed the concept of the digital thread, which illustrates how each of these models are individual strands that are tied together like a thread, so that when you pull on one and change one part of the individual model, it pulls through the rest of the models as well. And in order to achieve this vision, it really requires an ecosystem of commercial tools that all integrate together from day one. So what we've found is it just takes too much time and effort to keep developing custom tools at each phase of the life cycle and then trying to integrate them as you go. It makes it extremely difficult to identify those critical issues early in the process, which again limits your mission effectiveness. So having an organization-wide ecosystem of commercial tools allows you to quickly transition from program to program and not have to continually rebuild custom tools each time. And it also provides the added benefit of reducing the significant challenges of maintaining the custom tools, as well as transferring knowledge as individuals change programs or leave the organization. So we demonstrated a beginning part of this process in today's webinar, where we looked at some of these tools and applied that to a satellite constellation design. So we quickly built a mission model in STK, integrated it with an Excel cost model with ModelCenter, and ran some cost versus performance architecture level trade studies. And as you saw from the demo videos, they were probably only about 5 to 10 minutes each. So you're looking at about 25 minutes from scratch to do those types of trade studies, which talks to the 2.5 to 6 times of the timeline acceleration that we were talking about earlier. So having that commercial tool set that already is pre-integrated and is ready to use from day one is really a huge enabler of this digital mission engineering environment. And so I also wanted to say this is not the end. This is kind of just the beginning in this webinar series of the how to integrate things. So we've got the rest of the DME webinar series coming up. The next one is really going to do a similar deep dive into the SDK integration with SysML tools using ModelCenter. So that webinar is on August 13th. We're going to be integrating with Cameo through that MBSE pack that Joshua mentioned earlier. And we also have a follow-on webinar August 21st on extending SDK mission models with detailed Ansys engineering simulation tools. So we're really excited. We just have a new partnership with Ansys, and so we're going to be extending it throughout the program lifecycle into that detailed engineering design and get into some more higher fidelity simulations and show how to integrate that all together. So yeah, depending on how you answer that last poll question, some other next steps for you. If you're interested in more information or a demo from AGI, visit our website, agi.com, or email info@agi.com. And similar on the Phoenix side, you can check out their website, phoenix-int.com, or info@phoenix-int.com. We've got some other AGI events coming up. We have some virtual training. July 25th, tomorrow. We have the SDK Geosurveillance virtual training, where we'll go click by click through how to set that up. We have a radiation environment with SDK SEAT virtual training, and also a satellite collision assessment training on August 1st. And also on the Phoenix integration side, there's a webinar on September 10th on integrating MBSE into model-based engineering environment presented by Lockheed Space. So definitely check out those other events. And again, please register for the upcoming DME series, as we'll go into more detail on the SysML and the detailed engineering design phases of the life cycle.
And Jeff, if you don't mind me interjecting real quick, one other event that Phoenix is hosting, we have started a series of public trainings in our Novi, Michigan office. So we have a next round of those coming up in August. So if anyone would like to come to attend a public training, so send 6 people, it's up to your organization. Feel free to attend that.
All right. So I guess with that, that was all I had. I guess really quick to highlight it here. This is our contact information for myself and Joshua if you have specific questions. And just to highlight, so these are some of the products we covered today on the SDK side. So we really only covered just the tip of the iceberg. There's many other products that we're going to cover some of these, but if there's other parts or other mission sets besides constellation design that you're interested in, there's still much more to SDK, so you can visit our website, agi.com/SDK, to find out more about other parts of the software that we just didn't have time to cover with today.
And so the ones that you covered are highlighted in bold is what you're saying?
Correct, yes.
Yep. All right, let's move on to the questions here. There's quite a few of them, so if I ask you guys a question that is going to get too far into the weeds, maybe you could just say we'll take that offline and get back to the question asker independently. So real quick, let's try to get through as many of these as possible. When you were calculating the communication times in those cities, were you including any RF modeling?
No, in this case we were not. So we were using communication term kind of broadly there, and we were really just looking at the field of view of the sensor. However, actually one of the modules listed here, SDK Communications, allows you to provide the information for the transmitter and receiver and then do the RF link calculations from there.
Right, great. I think this next question is sort of an extension of that. It's pretty similar. How are radar search fences and other mission specifics modeled?
So yeah, similar to that. So you can either do a simple geometric sensor field of view. So the sensor object can take a variety of shapes and formats. So you can have it pointing in different directions. You can have different radar cells represented. So you can do it as basic field of view, or if you want to get into more of the actual radar equations, you actually can put in a radar object on your on the ground or on your satellite, wherever it exists, and then compute the radar calculations from there.
Okay, and so just for completeness, there was a similar question with OPA IR, so infrared sensors and their sensitivity and queuing and things. So similar sort of questions again, just real quick. What do you think?
Yep. So similar thing. So one of the sensor types is EOIR, electro-optical infrared, and that allows you to design your sensor and look at the radiometric performance of targets. And so that's how you would model that type of setup.
Thank you. All right. How does ModelCenter enable feedback and two-way communications for interoperability?
I guess that is a question for me.
Yeah, I'm not taking it.
So regarding feedback, so I guess it completely depends on the use case. But as far as interoperability, we do allow multiple tools, as we saw in the demo, to be integrated. So I would want to, unfortunately, I'd want to follow up with this question, I guess, offline, to get a little bit more detail about what they're thinking as far as the use case for this.
Got it. Now, another question came in is, I didn't see my tool listed. What other tools can be integrated? And I know it's probably a long list, but if you could just name some of the major ones, maybe?
Yeah, so some of the ones that come out of the box with ModelCenter, a lot of the CAD tools, let's see, NX and SolidWorks and a couple, let's see, CATIA. We have some others like MATLAB, Excel, some of the more common ones used. But just because those aren't the ones that come out of the box doesn't mean that other tools can't be integrated. We have an extensive list of tools that our users have created or developed plugins for themselves, whether they're in-house tools or COTS. So, like I said in the presentation, as long as you have a way to run the execution, whether that the tool has an API, can be run in batch, has a scripting method, and so on. Really, any other tool that you can think of can be integrated.
Great. Can you discuss the types of graphs that you have for showing multidimensional graphs and Pareto fronts?
Yeah, so we only showed the 2D scatter, but we have quite an extensive list as well, whether that's a 3D scatter or not. We also have settings and objectives and different things that we didn't get into the demonstration that can highlight those Pareto fronts and show multi-dimensional characteristics of our design space, whether that's the size of the bullet or the data point, the color as we saw, the opacity, and then we can even set objectives in our visualization, apply the constraints as we saw. So it's a pretty extensive list. I'd be happy to send more information or talk in person or give a demo on those other capabilities that we have.
All right, so Joshua, you mentioned a behavior model, and the question was, are you going to talk about that in a little more detail in a later webinar?
Yes, I apologize about that one. That was one of the next industry examples that we have coming up in the next webinar series that we're going to present. So I did misspeak by saying behavior when I was referring to the Parsons model, but we will discuss behavior integration or behavior diagram execution in the next webinar as well.
All right, here's one that I can answer. What's the difference between Satellite Toolkit and the new Systems Toolkit? Nothing. It's just a name. So a couple years ago, the tool was rebranded, and that Satellite Toolkit was the original software name 30 years ago, and it had added so many capabilities for non-satellite objects that it wasn't really representative of a lot of the use cases that people were, using it for. So the name was updated to be a little more accurate, and it changed over to Systems Toolkit. But STK, it's still the same thing, just a slightly different name. All right, so how are multiple models from different developers integrated?
So in that case, as we saw in the demonstration of integrating, STK and Excel, those components that we brought in could be technically hosted by another developer or another vendor or another supplier. ModelCenter has remote execution capabilities so that essentially we can have ModelCenter talk to other sites and pass very little data, essentially run the workflow, and then when it gets to the component that's hosted elsewhere by another developer, it will go execute that model locally on that developer's machine, giving the inputs and pulling out the outputs so that IP is maintained at that site. So there's actually quite a bit of interest around this, and that's what the Parsons distributed engineering focus really was on, was tying in different models from different developers, maintaining IP, and keeping a workflow consistent so that you could bring in sources from all and get a multidiscipline result.
Can you just real quickly touch on optimization in ModelCenter?
Oh, of course. I alluded to that ModelCenter Explorer has optimization built into it. So I think we have about 30 plus algorithms, whether that's genetic, gradient-based, proprietary things like DOT. We have a couple of legacy optimizations from Boeing in there as well. And then even if you have your own algorithm, that can be incorporated. So if you've developed your own optimization algorithm, you can plug that into our optimization tool and run a workflow optimization that way as well.
Great, thank you. All right, so question maybe for both of you, or I'm not sure. What do you see as the primary barrier to the implementation of an integrated MDAO system? And first, maybe define what MDAO is for some of the audience that might not know.
So I can take this one. MDAO, multidisciplinary analysis and optimization. So that is the look at integrating multiple disciplines, not just a single discipline into a workflow and running and getting ties in from all different disciplines. The biggest barrier that I've seen, or that Phoenix has seen, I believe, is not necessarily technology or the tools. It's more of culture or the adoption of that grand vision. So once you can get everyone to see the vision and to adopt it, things run very smoothly. So we've seen that at certain customers where they've adopted that in a cultural sense. Progress has been made quite rapidly.
Great. No, I think that's great. I think we're out of time here. So if we did not get to your question, we will follow up with you individually. All right. Well, thanks again, everybody. Our time's up. You know where to find us, agi.com/DME. You will receive these materials as a follow-up in a few days. And please sign up for the next one. From everybody here, thank you very much. Thanks for attending.
Thank you.
All right. Thanks, guys.